And the second talk in this session will be presented by Dr. Gengbin Zheng, and he is a research scientist in the Parallel Programming Laboratory, and he's going to talk about fault tolerance, in particular an approach to fault tolerance that is being developed.
This works. Okay. Hello, everyone. My name is Gengbin. I'm going to talk about some some progress in the last year about the fault tolerance support in Charm++. So specifically, this work is about a scalable double in-memory checkpoint scheme that we optimized for very large scale, basically towards Exascale. So a little bit motivation. So everybody knows that as the machine grows in size, the probability of, we get a lot more processor counts and lots of other components of the machine. And then the mean time between failure certainly will decrease. So for example, as we know that Jaguar, from like 2008 to 2010, someone basically measured the fault rate. And we observed that there's a 2.3 average failure per day. So if your application runs like for several days, you certainly you're pretty much certain that you'll face some failure during the execution. So the application has to to support fault tolerance in order to survive this kind of environment. As a machine right now goes to plan for Exascale, there are lots of new challenges come for fault tolerance. First thing is the disk. So the disk-based checkpointing is very slow. So as we know, typical disk-based checkpointing is you write your checkpoint files into a centralized NFS reliable disk, because you rely on some reliable media to store the checkpoint files. But that usually is very slow. And if you have an Exascale level machine, you would expect like very long checkpointing time to actually write to the files. Also, system level checkpointing also become a challenge. If the runtime, to do a system level checkpointing, the operating system normally has to do it very conservatively. So you have to dump all the process data and everything basically related to your job to the disk, regardless how usefulness is the checkpoints. So that basically tells us that for Exascale, typically is in favor of application level checkpointing scheme, so that the application can decide which data you want to write, and then you can kind of reduce the checkpoint size. Also, like we see in the disk-based checkpoint scheme, a centralized scheme certainly won't be a scalable solution for Exascale. So you need to design some scalable kind of scheme that can do like a distribute. You do the checkpointing and the restart in a distributed fashion to actually to make it more scalable and efficient. Another practical challenge is that on the nowadays supercomputers, the job scheduler will just kill your job if you're, say if one node failed or something. So even if the application can do fault tolerance, you don't have the chance, because the job scheduler will just kick your job out, and then you don't have any way of to deal with that. So this basically motivates the work in this talk, that we want to do some kind of a memory level checkpointing in a distributed fashion, and we think it's a fast solution and a very low cost, because we take advantage of the fast access to the memory and also the network. So in previous work, we have demonstrated that we call the double in-memory checkpoint scheme is very efficient. In 2004, we have a paper on this, and since then we have a production version in Charm++ for the last like 8 years, and it's always working in that fashion. So to give a very brief description of how this protocol works, I have this animation. So in this setting, The ABC up to J is the objects in Charm++. So they're distributed on here 4 processors. So if we pick one object, we know in order to tolerate a fault, here we're only targeting a single node failure in this animation. So if we want to support, if we want to survive a failure, then you certainly need to have 2 copies of the data in object D on 2 different locations. They can be in memory, they can be in local disk or SSD, whatever. But you need to keep 2 copies of this data in order to survive one failure. Similarly, other objects have been checkpointed to different locations, 2 different locations. Now, if we think the processor 1 crashed, then we live in the checkpoints in the lower half of the screen. So we can see we certainly lost the checkpoint for DE, ABC. But then since we have another copy on different other processors, so we can restore those objects from the checkpoints. Here's a D. So for D, we have 1 copy left. So we can pick the one process and then restore that checkpoints to memory. So we basically first reconstruct the lost checkpoints. And then out of these 2 checkpoints, we pick one processor to restore the objects. So the upper portion basically is the memory. And here are all the checkpoints. So this simple scheme basically takes advantage of 2 things. One thing is because for object D, we store 1 local copy. So that's a fast memory copy. You just copy to your local memory. And then you can use the high-speed interconnect to transfer D to the memory of another processor. So this will take advantage of the high-speed interconnect and also use the memory or the local disk as a distributed fashion so that it will speed up. So it's a very scalable scheme that it doesn't depend on any centralized storage. In Charm++, there's a few advantages provided by the runtime system. Nice features for fault tolerance. The first thing is we can automatically checkpoint threads. So to checkpoint threads is not easy. You have to checkpoint the stack. You also have to checkpoint the heap. In our scheme, we develop a thing called ISO-malloc. So in this scheme, basically we make sure that the threads will be checkpointed and restored in the same memory location. So no matter, even if you move to another processor, the thread will be restored in the same virtual memory address. So that all the pointers in your stack and your heap point to the same location. So the program will continue to execute without like having an invalid pointer or something like that. So the runtime will support this automatically. So all the fault tolerance support has to do is just to dump using the ISO-malloc scheme and dump the data into the disk or the file. And so it's a very easy process for fault tolerance to deal with the checkpointing because of the Charm++ support for pack and unpack of the user data. Of course, if you checkpoint the threads, something like that automatically, the whole stack needs to be checkpointed. So it's not very efficient sometimes. So some users may choose to write their own pack or unpack functions so that they can pick only the live variables. Those variables. For example, you can forget about the temporary variables. You don't have to checkpoint those variables. So the user can actually go through your variables and then choose the variables that you want to checkpoint. So those will help to reduce the checkpoint data. So the overhead of the in-memory checkpoint, as you can see, is because every object you have to checkpoint to 2 copies. So you basically will double the memory usage of your program. Surprisingly, there's a large class of applications that actually can tolerate this. For example, like molecular dynamics simulations and embodies. They typically don't have lots of data, so you actually can manage to do in-memory checkpoint for those applications. But we do recognize that there are some applications that you may involve a lot of data to checkpoint. So in that case, you can use we call a double in-disk checkpoint. So there's no change in the protocol. You just change the memory to disk. So you can write to the remote disk of another processor. But this relies on the fact that each compute node has local disk, which may not be true for some machines. In some previous results, we compare the double in-memory checkpoint scheme to the NFS disk. We have 5 different schemes, actually. So the first double in-memory checkpoint is using the MirrorNet to actually transfer the data, or using the 100 megabyte Ethernet, a slower internet, to transfer the data. And also we compare the scheme with the double in-disk, which use the disk instead of memory, and also the NFS disk, which is a centralized storage to store the checkpoint. As we can see, when we grow the checkpoint size from 6 megabytes to 6 gigabytes, and then we measure the checkpointing time for each case, notice that the y-axis is in log scale, so they actually difference a lot. So we can see the in-memory checkpoint using the MirrorNet wins all the way, actually, from 6 megabytes to the 6 gigabytes. I mean, this is expected because you are using a very fast internet. And we can see it's only take about, say, 5 seconds to checkpoint 6 gigabytes of data, versus in the NFS disk case, you actually have to spend 300 seconds to do one checkpoint of same size. So this is a very scalable and efficient solution. Interestingly, when we do the restart, we can see if in this scenario we have 128 processors running a small molecular dynamics simulation program running the APOE1 in this case. So when the program runs for a while, we kind of just log into the compute node and kill one process. And then after restart, because you lose one process, so the last checkpoints, the last objects on that processor will be migrated to another different process, and then you double the workload on a chosen whatever process. And then because that process you got double load, the load has been doubled, then the execution time, so the speed, the running speed will actually, it will run slow. So you'll see this arrays of the time per step throughout the rest of the execution. But if you apply the load balancing, so if you apply load balancing on 127 processors, so the load balancer will you will fix the load balancing basically using the remaining 127 processors, and then you will see losing one processor doesn't make much difference for your overall performance. So the program after load balancing will keep running at the same speed. Here's more stressful test. So in this case, we start with 128 processors, and then we kill 10 of the process randomly in the duration of the execution. So every time we kill it, the performance suffers, and then when load balancing come back, it will fix the performance. So after losing 10 processors, the job, you can see the program keep running at almost the same, just slightly slower. Doesn't affect the overall performance much in this benchmark. So this year we think because the machine goes much larger, so we want to demonstrate this scheme. We used to demonstrate this scheme on a cluster setting. Now we want to, for example, demonstrate this scheme on Cray machines and Blue Gene machines, which are much larger. But our scheme relies on the fact that you can actually kill the process, and the job scheduler won't kill your job. So this become a practical challenge on those supercomputers, because the job scheduler will just kill your job. So we kind of try to work around this to demonstrate our scheme. We just work around this by implementing this so-called fault injection scheme in the MPI, on top of the MPI machine layer. So we directly support the fault tolerance on MPI, assuming, just assume that the MPI, just pretend that the job doesn't die, and then we keep running the application with some faked kind of failure. So the way we did this is we introduced a function called die-now. The user can insert this function normally controlled by a random number generator. So you can add this function in your application, and then randomly this function will be called, and then the caller process will be, basically the runtime makes sure that the caller process will just freeze by, for example, calling a dummy MPI functions. So you never receive some message. So the MPI function, for example, you call MPI receive, and then that process will just stop there, never proceed. That will pretend that this MPI process died. And then we introduced this fault detection scheme by sending, basically each pair of processors will send a keep alive message. So if the body processors send a keep alive message to this died processor, and this died processor never respond, then the body processor will announce that this MPI rank basically dies. And then it will trigger our fault tolerance protocol, try to restart. So to restart, there's no way we can spawn, a new processors. So we do this spare processor idea. So when we start an MPI job, we leave aside a few MPI ranks only for the fault tolerance purpose. And when one process died, faked died, we pick one process from the spare processor pool, and then we trigger it by sending an MPI message to activate that MPI process, so that it will actually go into the Charm++ scheduler. So start to schedule message, and then basically activate that MPI process for Charm++ usage. This scheme is very realistic. Except for the fault detection part, all the protocols are the real in-memory checkpointing protocol. So we basically keep everything else remain the same, but only pretend that that process died. That part is a faked part, but everything else basically is the same fault tolerance protocol. So using this technique, we actually can demonstrate the same protocol on a 64K cores of BGP machine. So we can actually show that the fault tolerance actually works on BGP. But at the beginning, we just run our original protocols on 64K, up to 64K BGP cores. We see that the performance is surprisingly good. Even for 64K running, this is LinMD, it's a small molecular dynamics application. For 1 million items, we only take like 0.8 seconds to checkpoint. Admittedly, molecular dynamics simulation has very small memory footprint, so the checkpoint size is not big. But still, we can see there's only 0.8 seconds to checkpoint the whole application. And then the restart time is only take like 4 seconds for 64K cores. However, the problem here we observe is that both the checkpoint time and the restart time actually scale with the number of cores. This actually a little bit worry us, because if you go to the Exascale, let's say 1 million cores, which is 16 times larger than the 64K, then we will spend like about a minute to restart this small application. So that's actually something we want to optimize. So we actually went through the protocol and then check where we actually lose time in our checkpoint and restart scheme. So it turned out that we found there are a few bottlenecks that actually cost us like OP of time. P is the number of cores. So the first things we found is for the collectives, there are a few barriers in the protocol, because the barrier need to be placed to guarantee the different phases. For example, you have to remove the old objects, and then you restore the object from checkpoints. So you need the barriers to basically guard different phases. And originally, we used a barrier that is I mean, we have a tree-based barrier, but because our original tree-based barrier doesn't support a failed node, so the tree may have like a holes in the tree, so that we didn't support. So we actually use a very simple barrier of everyone sent a message to processor 0, for example. So this certainly cause a very it's like a OP of complexity. So this actually will cause a bottleneck for the protocol. It doesn't show up. The performance, I mean, the bottleneck doesn't show up for small processor count. But like we see in the previous slide, when we go through 64K, we start to see the impact of this this expensive barrier. So of course, the optimization is just to switch back to the tree-based barrier, and then we basically get it down to the log P of complexity of doing this barrier. So that helps a lot for the for the overall performance, which I will show in the next slide. Another thing is on a very large processor setting. When the restart happens, one processor died. The program, the other processor will keep going. So they doesn't know that there's a processor died. So they will keep going, and then they will keep sending messages, because the communication can be localized. So you have to apply a throttle as quick as possible, so that everyone knows there's a failure, and then everybody stops sending, I call stale message. So because those messages are useless, your program has to come back to the checkpoint. So any message sent by the other processors, they are useless. So one way of doing this is to introduce an epoch number. So when the processor died, so every processor will advance their epoch number. So the message will be stamped with an epoch number, and then if a message arrives with an old epoch number, they will be discarded, because those are messages from the previous phase before restart. So those messages need to be discarded. So like I said, I mean, in a large processor count, lots of stale message will fly around. So you have to throttle it as quickly as possible. So basically, we just implement a dedicated phase that every scheduler, so the scheduler on every processor will just keep discarding the stale message until there's a quiescence, which means there's no more message on the fly, so that we can quickly get into the restart phase. So this helps a lot to actually to basically advance the restart protocol by discard the useless message. Another thing is for basically this is also a communication issue. So if in a large processor settings, you have to send a lot of control message in the restart protocol. For example, every object when you restore the object, you have to send a location message to tell the whole processor that I'm now living on this processor. So this kind of small message will be fly around in the protocol, and then you basically will suffer a lot, because there's small messages is very costly if you send a large number of such messages. So one optimization we did for this is to apply a streaming optimization, so that you can combine the message to the same destination processor, and then you send one big message instead of lots of small message. This will improve the network performance and doesn't kill the restart. I will show a few comparisons of after optimization. We can see for the checkpoint, the left is the before optimization, and the right is after optimization. So we can see the time, we kind of improve about like 20 times faster by just doing the previous 3 optimization. And instead of going like an OP linear, grow linearly with the number of cores, right now the curve is relatively flat. So that's very scalable up to 64K cores for checkpointing performance. And we also demonstrate for the AMPI, this is Jacobi, which has a little bit larger memory footprint, which is 19 megabytes per core. We also observe this flat curve up to 32K is on Kraken. Or the previous one is on BGP, is Intrepid. And this one is Kraken. So we can demonstrate on both supercomputers. And for restart, again, this is on Intrepid. For 64K, we used to see this linear growth. Now we still growth, but this is pretty much like a log P growth after the optimization. And we can see from 4 seconds, we now optimize to only 0.15 second for restart, which is amazing for 64K cores. Only take like 150 millisecond to restart the whole application. Okay, so in conclusion, that we see that there are lots of potentials for this in-memory checkpointing fault-tolerant scheme. After optimization, is very scalable, and we expect it to be good for Exascale, even for Exascale level of environment. And we also and a short paper is accepted on the FTXS workshop. We'll be presenting this work in June next month. Future work is we will do this non-blocking checkpointing. So right now it's a coordinate checkpointing. So the program will only resume after the checkpoint finish. So for non-blocking checkpointing, we will basically leave the checkpoint data aside, and then having, for example, a different thread to actually transfer the checkpoint to the destination in the background, so that the application can resume. So this will further reduce the checkpointing time, hopefully after applying this optimization. Okay, that's it. Any questions?
So you mentioned the need to implement your own method for killing, like pseudo-killing jobs to test, because the job scheduler would shut down your whole job if a process died. Right. So what do you think the prospects are for getting people to actually change the job scheduler so that this can be used more in practice?
Yeah, but that definitely needs a change in the job scheduler. So the job scheduler basically have to give the application a chance, right? So basically, so you basically need two things to actually make this a reality. So first thing is the MPI library need to be fault-tolerant. So if you kill one MPI rank, the MPI library should still survive. So that's not the...
You don't mean MPI, you mean the communication layer.
Yeah, the communication layer, the hardware.
Could be the UGINI.
Could be UGINI, but the MPI also need to survive, right? The MPI on top of UGINI.
So if charm process is implemented on top of, not on MPI,
I'm
but...
talking about the MPI, charm on MPI. If charm on UGINI, that's a different story.
Yeah.
Yeah, and also the job scheduler need to basically, I don't know, I mean, there one way or another, the job scheduler need to tell the application that there's one MPI rank failed, and then basically give a kind of, you know, a fault indication to the application to actually start a protocol.
Just one comment on BlueGene P. In the past, IBM had a high throughput mode, where the purpose of the high throughput mode was so that jobs could actually essentially exit and then keep the node and run another, another binary. And so there was a little wrapper. And I think, Jeff might have tinkered with this as well. There were several people at Argonne working on doing a series of benchmarks with that. So it might be something you look at, is using that, because then you can essentially keep the nodes, because HTC mode does not, you can exit and then it just lets you, execute another piece. So yes, all the job schedulers need a way to say, continue execution, and that's just something we can, ask the vendors for. One last question though. When you're doing in-memory checkpointing, you still, at some point, want to do a disk-based checkpoint for when the entire, machine crashes at some point, right? So you have to...
the entire machine. Like I said, we are mostly target for single failure, or maybe the multiple failure if they are not.
Actually, you still want to, in addition, have a disk-based checkpoint.
Oh, yeah.
I mean, so you have to swap between. You have to do both, right? I mean, your method shows how fast the memory checkpoint is, but of course, you know, the system can still go down for other reasons, and you don't want to, you know, have to start completely from scratch. So, you know, can you imagine, you know, choosing those two parameters, both how often you write something out to disk versus how many, you know, times you keep it in memory? Does that make sense?
Yeah.
So Charm currently supports in-disk checkpoint as well. So the question is, can you specify do in-memory this often and in-disk every 20 minutes?
Actually, right now, the frequency is chosen by the user. The user decides when to checkpoint.
You combine both.
Yeah, you can combine both. Those two, there's the two different function calls. One is to do the memory checkpoint and one is to do the disk. For disk, basically, it will dump into a centralized. It needs to be a centralized, reliable disk. So it doesn't do the double disk kind of scheme.
This protocol can work with a spare or without a spare as well, right? Can you comment on that?
This scheme actually works for both. So in the slides I showed earlier, like I killed it 10 times, that's without spare. So I kill it, and then you keep losing processors. And then the slides at the end, basically I show with a spare processor. That because that's for MPI. I have no way of, I mean, basically I just choosing spare processor from a spare processor pool to replace the failed processor. So both way is controlled by runtime, so you can choose different kind of scheme.
If you Google on HTC and BlueJean, you'll find papers.
Okay.
It allows you to do persistent memory mapping, so that if you want to do an in-memory checkpoint, you could hang it and then start it back up and be in place.
Oh, I see. So you mean the job can be killed and then I can restart to use the same memory?
Yeah, from job to job, you can keep something in memory in a persistent.
I see. Oh, okay. That would be useful. But right now we are just basically doing we are not doing a turnaround and type of fault tolerance. We just let the job continues. But we can still use this. Yeah, we can still use this scheme to do it. Yes.
Okay. Let's thank our speaker.